Okay, good morning. I just started the recording and I want to put it on record that I do want to encourage people to, of course, listen to the recorded version of the lecture for if it helps you learning, but not being here either virtually or physically here is not an option, and those who are not in the class and listen to it later on, just pay attention to this, okay? Technology is there to help us, not to encourage us to abuse the facilities and the privileges. All right, I did put up the project list finally, and has a suggestion of about 20 projects, and it is on modal. So some of them have already been taken, and I'm doing it by first come first served by email. Okay, so please send me an email. I'll use the email stamp to determine the order. But if two people want to work on one particular project, talk to me about it. By email I will know, I will talk to you, because we can always find variations on this. Okay, so, and what I expect from the project are the following. I have already kind of highlighted here a brief literature search, not an extensive one, because some of these projects will have thousands of papers on them. I don't want you to produce an extensive literature search, but you must have at least 10 papers related to that in your bibliography that you have read, and preferably selected over a period of time, not all 10 papers in the 1950s, but maybe one from 50s, two from 60s, three from 70s, or something like that. Spread it out so that you get an idea of how that particular problem has evolved over a period of time in terms of the difficulty, in terms of the depth, etc. Okay, so that's one key element that I will be looking for in the project report. What I want to get from you on this project is a report by first week of May, and a presentation in the first week of May that we will schedule. For those present in PI, it will be online, so we will use the same mechanism, but I will hand over the presentation control to you, and you will just have to run through the PowerPoint and make the presentation. And everybody else in the class will be given a grading sheet, so everybody will grade the presentation for quality of the slides, quality of presentation, etc. But ultimately, I will decide how to weight that particular input. Okay, so a report, a presentation, and an oral exam, which I will schedule individually with each one of you, lasting maybe about 20 to 30 minutes, not a long one. And I will, in that oral exam, ask you questions about whatever we have covered in the course, plus whatever you've done in the project. Okay, I just want to see that you have understood the basic concepts and you're familiar with it and comfortable with using the tools. Okay, so variations on the project. How would you do this? How would you extend it this way? You should be able to defend your choices you made for boundary conditions, type of polynomial approximations, etc. Okay, so those are the three things that will be centered around the project, which will be a significant part of the weight. And then I will continue to give you assignment. In fact, this week I will put up the next assignment. I'm going to talk about a specific problem today. And those assignments are the ones where you actually learn programming skills a little bit in implementing some of these advanced algorithms. Okay, so there may be 4 more assignments like that. I won't give you too many assignments. We have had one so far, right? So probably a total of 4 or 5. It won't be more than that. Okay, and these are the only assessment tools. There is no exam or anything else. And the project report itself should contain a brief literature review and detailed problem formulation. That's very important. Okay. So that should include the equations you are going to solve, the domain, the geometry, the boundary conditions. Everything has to be identified. And the solution, typically using COMSOL, but I'm not going to force you to use COMSOL. You can use Fluent, you can write your own code in MATLAB if you like, or C++, it doesn't matter. Okay? But that problem has to be solved using a computer it's okay to use commercial tools or open source material. If you want to use OpenFOAM, that's fine as well. Okay. And in each report, there must be at least one figure from the paper that you are reading. Of the 10 papers that you read, I've given you one in each, but pick a paper where you want to reproduce some of the results. Okay. So pick one figure and superimpose your computation on that figure. I want to make sure that you are able to reproduce an existing literature. And for this one, you can pick a 1950s paper if it is easier. Okay. The only difficulty is, for example, if you take the flow past a square cylinder or a circular cylinder, okay, you will find, as I said, thousands of papers. And the early ones would just simply point out how the flow breaks up. So here you have a cylinder. Okay, so the flow at Reynolds number of maybe 40, maybe like this, very steady, two-dimensional, and there is a wake. And you might find where that separation streamline is and what is the length of the wake as a function of Reynolds number. Those are the kind of computations you will find in the 40s and 50s and 60s. If you go to 70s and 80s, the same problem, you increase the Reynolds number, and you will find something called vortex shedding, time-dependent flows. Now it becomes two-dimensional time-dependent flow. You go to 2000, you'll find the same problem, but it'll be now looking at perpendicular to the board what happens to the flow. Because all the two-dimensional flows will assume that if the flow in one plane is like this, any plane will be the same. And people have done experiments with the length to diameter ratio of the cylinder of 40. In an experiment, you have to have finite length. You can never have infinite length. But this is an assumption based on all the two-dimensional solutions assume that it is infinitely long. But in reality, what happens, that translational symmetry perpendicular to the board is broken. The flow becomes three-dimensional. It develops another wave. Okay? So there are computations on the transition from two-dimensional to three-dimensional flows, stability analysis and stuff like that. So for comparison purposes, you may want to take an earlier paper which doesn't have such a complex physics. But what you should get from this course is the complex nature of the physics and the tools that are used to explore them, and a little bit about the numerical tools that we are going to talk about throughout the course. Okay? So that's just an example. Every problem that you have will have more complicated physics as you excite the system with higher and higher forcing term. In this case, it's simply Reynolds number based on the approach velocity. Okay? And then people have looked at what happens if I have two cylinders next to each other, or three cylinders, different arrangement. So the literature is very broad in that respect. Okay? So pick one problem and present that. And then I also want some results on grid independence. What does that mean? Because we are solving these problems numerically, you need to construct a numerical grid. And if the grid is very coarse, there are lots of numerical errors. We will be talking about them throughout the course. In fact, I will talk a little bit about it today, just so that you understand what I'm talking about in terms of grid independence. So you should have some results of grid independent tests. It simply means the problem that you take, you solve it using 100,000 grid points, and then resolve the same problem using 200,000 grid points, and see how much the results have changed. And what you will find is it changes less and less as you have more and more grid points, because the discrete version of the solution approaches that of the continuous solution, which is the partial differential equation. Okay? You should document all the changes that you have made, choices that you have made in the numerical algorithm. Why did you choose conjugate gradient? Why did you choose LU decomposition? Whatever choices that you made, okay, for second degree polynomial or third degree polynomial approximation, etc. Those things hopefully will make sense as we go through the course, as we see the approximation methods. But you will probably have to start making those choices before we actually cover it in the class. Okay. So if you can suggest any other topic, okay, just let me know and get it approved, so that we don't get into a problem in terms of scope later on. I want to make sure that you're tackling a reasonable problem for this course that's comparable to all the other students' efforts. Any questions? 8, 2, 4, 6, 7, not bad. 15, 16. Somehow we reached a total of 60. I think there are about 19 people registered in the course. I'm just concerned about people not attending the course. So I just will take a quick survey who are all there online. So any questions from here on the project? So send me an email as soon as you get a chance to look at it. There is one reference on each project, I think. Some of the projects on two-phase flow with droplets, Ronald has picked them up. Some of them I have picked simpler ones using just single-phase flow. So in the last lecture, we talked about concepts. I mean, my goal in this course is to give you introduction to some advanced concepts on stability and multiplicity, and then learn how to solve such kinds of problems using fairly advanced numerical tools. We are not going to be developing these tools in this course. That's why we are embracing COMSOL very comfortably. MATLAB and COMSOL you should be able to use. So the assignments, I will expect you to use MATLAB so that you can learn a little bit of programming and implementation issues. Same problem can be solved with COMSOL also. Ronald will show you how to do that. So we talked about the concept of Lyapunov stability and a few types of multiple solutions, the so-called supercritical pitchfork bifurcation, the fold bifurcation, and the subcritical pitchfork bifurcation, and the cusp in a two-dimensional parameter space. And we saw what is called the Lyapunov second method of stability, that is how to determine stability of a system, of a dynamical system, even without solving what the state is as a function of time. So all we need to do is find, I mean it's easily said, find a function v that is positively definite and its time derivative is negative definite. Then you know that equilibrium system is stable. And we saw a little bit about the region of attraction. These concepts are very important because when you're solving using COMSOL and it doesn't converge, the first thing that should come to you is, of course, am I doing anything wrong in setting up the problem? Assuming that you have set up the problem right, is my initial condition, is my initial guess reasonably close enough to the actual solution? So the methods that we're going to talk about today guarantee that you'll always be close enough to a real solution. And we saw about linearization of a nonlinear system. That's the core of solving any nonlinear problem. Linearize it, then use the linearization tools, but do it locally. Okay? And we saw Newton method in particular as an example of linearized iterative methods. So the problem, just to recap, is give me dx dt equals some function of x and p. X is the state variable, and it could be a vector of any length. Okay, and p is a parameter set, Reynolds number, Grashof number, Schmidt number, whatever. And that is a dynamical system, and it is an autonomous system if t does not appear explicitly in the function. Okay, and what that means we talked about in the last class. If t does not appear explicitly in the function, then the trajectory is determined, and if your initial condition is anywhere on the trajectory will be the same. Okay, so you can shift, time shift the solution, and it will be invariant to time shifting. And you need to have a set of initial conditions. X at t equal to naught is x naught. And the solution to this means, the dynamical system means find x as a function of time. So starting from initial condition, you might have a steady state, or you might have a periodic state, or you might have a chaotic state. All these are possible responses to the dynamical system. And the Lyapunov stability will consider all these to be stable, because all it says is, if I start from somewhere near an equilibrium point, it must be bounded. So I can always put a bound for the response on this one, for example. So that will still be considered as a stable, chaotic response on that. This is a stable, steady state because the time derivative drops out. But in here, the time derivative doesn't drop out, okay, but it remains bounded. So something like this will be called a limit cycle with a very regular, periodic, repetitive fashion. All such responses are possible from that equation. But before we get into the dynamical responses and the algorithms for finding the solution, we want to find out what is the steady state. Okay, and the steady state is obtained by setting f of x p equal to 0. So that is a nonlinear algebraic equation that we need to solve. Now the solutions for these is just a vector. X would be a vector in the state space. But that solution can change. In fact, this dynamic solution can also change if I change the parameter. Okay? So I would get different response curves for different values of the parameter. It might happen for low value of the parameter, I get a steady state. I keep increasing the parameter, it goes into a periodic state. And I keep increasing it further, it goes into a chaotic state. In fact, that is thought to be one root of how the Navier-Stokes equation gradually loses stability towards turbulent flow. And turbulent flow is nothing but very highly chaotic flow with all frequencies of oscillations that are possible. So we need to learn a little bit about how to represent the signals that are either periodic or chaotic. Okay? But for steady state, the same thing applies. I can track how this solution X changes with P. Okay? I can plot such variations, and that is what is called a bifurcation diagram. Okay, so here we are plotting the state of the system, some norm, some measure of the system X against a parameter P. It could be a Reynolds number. In most of the projects that you do, it could be just Reynolds number. So you might find that the solution goes like this, and then turns back and goes, and turns back and goes, and there is a fork there, and there is an isola there. All these are possible responses to the steady state problem. Okay? What does that mean? If I take, for example, certain values of P, there are 3 solutions possible. Okay? Some other values, there is only 1 solution possible. Okay? And in this window again, you have 3 solutions possible. And in this window you have again 1 solution possible. Okay? So how would we construct such a solution path for X as a function of P is what we are going to talk about in today's lecture and the next lecture. The tools for constructing such a path and the tools for locating exactly where these critical points are. Okay? What ideas do we use to locate such critical points? And these algorithms have been developed in the 80s only, okay, fairly recent compared to the Newton method and some of the earlier numerical methods. Any questions? Is it clear? I'm trying to set the agenda of what we are trying to develop, and then we are going to actually go ahead and develop the tools for constructing such a diagram, and your next assignment is going to be on this one. I guess Mrinal showed you on the CSTR problem with 2 equations. Did he? Do you remember? Mrinal is probably there. Mrinal, did you do the reactor problem for them when I was away?
Yeah.
This is also a check for you guys to see whether you are paying attention. You started on that. Okay. But could not complete the arc length. All right. Okay, that's fine. So maybe I can make that as the problem for them. I was thinking of another problem. But let's talk about the ideas, and then you will get one problem which you will use to construct solution paths like this. Okay? So if you give me a value of the parameter, then I have simply f of x equal to 0. Parameter is a constant, it's a number. How do I solve such problems? That is using the Newton method. Okay? So the very first algorithm that you should know is the Newton method. And in the last class we talked about it as a method based on linearization of the function around a certain particular guess. Okay, that is about a particular guess. So the method itself is something like x at the n plus 1th iteration is equal to x at the nth iteration minus j inverse f. And j is called the Jacobian of that function f, and xn is the initial guess that you make, and f is the function that you calculate. Okay, and we also saw in the last class that I can think of it we saw that you can think of it as solving this linearized system. So you write this as xn, for example, plus delta n. The delta n is the correction to the initial guess that you make at the nth iteration, and the correction comes from solving this equation, j delta equals minus f. So essentially what you're doing is you are solving a linear set of equations, n going from 0, 1, 2, etc. So here it is an initial guess. When n is equal to 0, x0 is an initial guess. And you take that guess, plug it into the function f, you can calculate the function, it's not going to be 0. If it is 0, then delta will be also equal to 0 as long as j is non-singular, right? So that is a key point I want to come back to. So that is called a regular solution. If j is invertible, then j is not singular, then you have a regular solution. So as the function goes to 0, the correction goes to 0, and xn plus 1 is the same as xn. You have converged. Okay? So you need to write a code. In fact, the code for Newton method is available in the textbook, I think, that I put on Moodle. So you can just copy that. And you need to write the function. And you need to write the Jacobian matrix. The Jacobian matrix will simply consist of all the derivatives of the function f1 with respect to x1 all the way to f1 with respect to xn. And similarly in the last row it will be dfn with respect to dx1 going all the way to dfn with respect to dxn. Now for large system it might look like it is a lot of effort, because if you have 20 equations you need to have 20 derivatives for each equation, so 400 elements that you need to evaluate what the derivative looks like. Okay? And it might look like it's a tedious job, but there is often a pattern, so it's not that difficult to solve, evaluate the Jacobian. And you need to write the function. So you need to provide two routines, subroutines or functions that the Newton method will use. One, it will expect to return the function value, other one the Jacobian. Then it solves by LU decomposition, Gaussian elimination, whatever this linear problem, and then puts back the correction and converges. And Newton method converges quadratically as long as you have a regular solution, meaning J is invertible. Okay. So this is crazy. I am picking the right one, but still I'm not able to move it forward. Okay, so Euler-Newton continuation. What is that idea? So remember, we talked about constructing the solution for x as a function of p. So I'm taking one value of p and applying the Newton method, and I got one solution. There is one point. Now I want to, and this I got by simply luck, because I need to make an initial guess. Okay, so if the initial guess, and when I make the very first solution, I don't know whether I'm close enough to the real solution or not. My initial guess is purely arbitrary. So I need to play with it until I get a converged result. And we will see we can always design a problem in such a way that the parameter, for small values of the parameter, the problem becomes linear. In the Navier-Stokes equation, if Reynolds number goes to 0, you have a linear system, right? Then there is no problem with convergence, because linear systems have solutions and you can converge easily. So the very first solution that you should get typically would be for a very small value of the parameter. Then I want to make sure that when I solve for the next value of the parameter, somewhere here, okay, all I'm doing is I'm incrementing delta p by a certain value, my parameter by a certain value. I want to provide a good initial guess. What would be your first instinct to give as an initial guess for the next value of the parameter for this solution? I'm going to try to generate the solution. I have this solution already by hook or crook. Just copy that, right? What that means is take this and give this as the initial guess for the solution, and make sure that your delta p is small enough, right? Because hopefully the solution curve would be a smooth one like this, right? So if you make delta p small, the increment that you're going to change is going to be also small. So that will always remain a good guess. Okay, and that is called a simple continuation. Okay, you are continuing using a previously converged result as initial guess for the next value of the parameter. What would that method do? Suppose you are somewhere here and your next guess, you don't know where that point is going to turn, right? So you have kind of continued and branched up, come up to this point, and you are making the next step in delta p. And there is no solution. What do you think would happen? But there is a solution way ahead somewhere, right? So you are saying this is going to be my initial guess, right? Using that initial guess, find a solution for that value of the parameter in that neighborhood. And there is no solution in that neighborhood, but there is a solution far away, right? You might find that it jumps to that solution if it is within the region of attraction of that solution. This is why the concept of region of attraction is important. Okay? So if this initial guess is within the region of attraction of the solution, if you give it maybe a sufficiently long iteration, it will get there. If it takes, for example, 3 iterations to go from here to here, to go from here to there, it might take 100 iterations. Okay? So that is a problem that we are going to address, how to overcome that. This is what we call the arc length continuation. Mrinal will demonstrate sometime later on. But before we go there, let's go back to this and ask the question, can I do better than this? Instead of saying the previously converged result is my guess, can I say, can I come up with a better guess that is closer to the real solution? And the answer is, if I know what is the tangent vector dx dp, what is the tangent vector dx dp? If I know that, then I can say my next guess at x at p plus delta p is going to be equal to x at p, help me complete that, plus dx dp at that value of p multiplied by delta p. What is this? This is the Taylor series expansion for the solution x as a function of p, treating it as a continuous function of p, right? So if we neglect the second term, we have a simple continuation which simply says take the previous solution and that is the guess. So this is the guess. For p plus delta p. So if I truncate it after the first series, then it says just take the previous solution and use it as the guess. But if I take the next term, it says take the tangent vector at p and multiply it by delta p so that you get the delta. What would that give you? That will give you a delta x, right? That is the increment from the current value that will take you closer to the real solution. And this is called the Euler-Newton continuation method. Okay? Once you see that, and a lot of numerical analysis is nothing but Taylor series applied repeatedly, right? Newton method was from a Taylor series approximation, linearization. So this is the that was a linearization with respect to the state x, f with respect to x. This is a linearization of x with respect to p. The solution of x with respect to p is a highly nonlinear curve, but we are saying locally if I can linearize it, I can get a better guess. Now this is only a guess. After you get that, you need to go back and use it with Newton method to actually converge. But you'll find Newton method will converge in 2 or 3 iterations if you apply this method. Okay. Now the question is, how do I get the dx dp? And if you get that, you grasp everything in this course. There's really nothing more that I can teach you. It's all application of the repeated application of the same idea. Okay. So my question is, how do we get that vector dx dp from the original equation that is given to us, which is f, which is a function of x, but it is an implicit function of p. That is a recognition that we need to make. But it is also an explicit function of p. What does this mean? This is the same equation that I wrote earlier as f of x comma p equal to 0. But I didn't indicate explicitly that x will be changed by changes in p. Of course it will be, right? Because if I change p, the solution changes, right? And the solution looks like that. So if I make this connection that f is a function of x, but x is a function of p implicitly, but it is also a function explicitly of p. That is, p appears directly in that function. Okay? If I know that, then I can apply the chain rule to take the derivative of that function. So if I take the derivative of that function, how will it look like? df. I'm taking the derivative of the function with respect to p, and it should also be 0. The function is 0, its derivative with respect to p should also be equal to 0, right? So when I take the derivative with respect to p, first I need to take the derivative with respect to x, and then multiply it by dx dp. That is a chain rule, right? What would be the second part? df dp. That is equal to 0. Let's pause here and make sure that everybody is comfortable with what I have written there. Okay. Guys online from everywhere, are you following me? Any questions? Multiple attendees, everybody is asking questions. Okay, looks good, fine. Did you understand the last part about the chain rule application? Any questions? Okay, good. Looks good so far. That's good. So let's go back then. So this is recognizing that if I make a change in p, it can directly change the function f because the function depends on p, but it can indirectly change the function f because p changes x and x changes f. P changes x, which is captured here, and x changes f. So this is the total change in f due to change in p. That's a total derivative of that function with respect to p, and that is equal to 0. And you should keep track of what is vector here and what is a scalar. Okay, which are all the ones that are vectors? F is a. I cannot change to anything. I'm stuck in the back. It shows me a change there, but it doesn't allow me to do anything other than. Okay, so this quantity is it a scalar, a vector, or a matrix? F is a vector, x is a vector. There are n variables and there are n functions. We're talking about n by n equation, right? So that is going to be my Jacobian matrix. There is nothing but the Jacobian matrix. We have already calculated that. When did we calculate it? In implementing the Newton method. Right? So we already know what the Jacobian is. We have calculated it. We have a converged value for that at the previous solution. And what is dx dp? That is what we want, right? We want dx dp. Okay? So that is the unknown in that equation. And what is df dp? There are n functions. Each one of those functions will have p in them. So you can take its derivative. So it is a known derivative of size n by 1. Okay, so this will be n by n, and this will be n by 1. So what do we have here? We have a system of linear equations that we need to solve. Okay, so from this one I can write dx dp as a vector as equal to minus j inverse df dp. So that gives me what the dx dp is, which I can use it in here, and it will give me a better initial guess that is projected along the tangent line. And I want you to implement that on one of the problems, the Euler-Newton continuation. The beauty of this method is that I have already solved for J, I have already calculated J, I have already inverted J in solving the Newton method. So if you are efficient about it with LU decomposition, all you need is one extra back substitution for a new right hand side. Okay, the LU factorization that you did can be stored, and one back substitution will give you this estimate of the vector. So it's extremely efficient computationally, particularly for a very large system. We have implemented this when in the 90s we did some paper with about 200,000 equations. That is, you're taking Navier-Stokes equation, discretize it, you end up with 200,000 algebraic equations, nonlinear. Okay, so we just implemented an LU decomposition scheme for sparse matrices, and it was extremely efficient. Works very well. When does it fail? It fails when you are near the turning point. Okay, so when you are near this turning point and you are still projecting a tangent vector like this, right? So that doesn't do anything because your initial guess is still nowhere close, because there is no solution past this critical value of that parameter P. Okay, so the Euler-Newton method will also fail. And the question then is, what do we do? Any ideas? Why does it fail? Why does it fail exactly at this turning point? It turns out at such turning points the Jacobian is singular. There is one eigenvalue that is 0, so you cannot invert that. Okay? So all these kind of work together. And the question then is, how can I make a problem that makes this Jacobian regular and you can just turn around? And the idea is called the arc length continuation. And what it does is, it poses a challenge. It says, why do we need to treat P as a parameter? Simply because it appeared naturally in the problem, we just picked it. Okay, but for a mathematician, it doesn't matter. P could be anything. So make P as an unknown. Okay, so the solution to this was done by an applied mathematician from Caltech called Keller. So it's called Keller's arc length continuation method. Before that, a Russian mathematician in the 50s developed a very similar idea. It's called the Davydenko's method. But the basic idea is the following. Why do we have to treat P as a distinguished parameter? Why don't I make P as an unknown? That means I have an extra degree of freedom. Instead of n equations, I have n plus 1 equations in here. Okay, but I'm going to introduce a new parameter. So I'm going to reparameterize the problem. Because I have an extra degree of freedom to solve for P, I can put an extra constraint. Because I need to have number of equations matching the number of unknowns. I need to have a well-posed problem, right? So if P is fixed, then I have n by n problem which is well-posed, except for particular critical values of P, this method fails. Okay? So the idea is I'm going to make it into an n plus 1 by n plus 1 system and treat P as an unknown, but introduce an additional equation that will reparameterize the problem, meaning it will have a measure of the length along the curve as a parameter. Okay, so this is the extra degree of freedom that I have. I'm going to prescribe an equation. I'm free to prescribe the equation any way I want, and I want to prescribe it in such a way that I overcome this problem. Okay, and that's called the arc length continuation. So the idea is, I'm going to make this as n plus 1 unknowns, and I'm having n equations. I'm going to add an n plus 1 equation. Okay, and that equation is I'm going to write down right now. I just want to maybe get rid of this and restart because it's annoying. Not able to move this. Just give me 1 minute. Hopefully it will work. hopefully. Better. Okay. So as I said, I'm going to add the extra equation, and that equation I'll write it down, and then we'll explain what it is. So it's going to be something like summation I going from 1 to n, some weighting function xi minus xi naught square plus square plus w2 times p minus p naught square equals s minus s naught square. What does the equation look like to you? It's a circle, hypercircle, whatever you want to call it, in an n-dimensional space. Okay, so this is your reference point. That is the current converged solution, and so we know that. Okay, what the current value is, I'm going to take that as a reference point. The complete vector x and the parameter p. Now I have n plus 1 unknowns. So my unknowns have become x comma p. X has n unknowns and p has 1 unknown. So I have n plus 1 unknowns in total. And the right hand side is the radius. Right? What is the equation for a circle in a two-dimensional situation? X minus x naught square plus y minus y naught square equals r square. Right? So it's a generalization of that. It's a generalization of Pythagoras measure of distance, if you like. So what actually we are saying in conceptual terms is the following. That is my n plus 1th equation. Okay? This is my n plus 1 equation. So I have now n plus 1 equations in n plus 1 unknowns. But what is the parameter I'm going to specify? I'm going to treat this as a known, the radius. Okay? And I'm going to treat these as unknown, xi and p. So now I have an extended system of n plus 1 equations in n plus 1 unknowns. I can apply Newton method on that, and I should be able to get a solution. And Murad will show you how to implement that in COMSOL in a very nice, elegant way. And we will see how to do it. You will do it in MATLAB. Okay? So the geometrical interpretation for that is the following. Okay, so here is the parameter p, here is the state x, and I'm going to exaggerate. The solution is like this. Okay, so here I have my current solution at p naught, and this is x naught. That's my reference point I have identified here. P naught is known, x naught is known. That is where I have my last converged result. Okay, and if I apply a regular Euler-Newton continuation, I'm taking a tangent and I'm saying find me a solution there. That method fails. We know that. Okay. So what we are saying in this reformulated problem is the following. So here is my equation, the n equations, f of xp is equal to 0. These are the n equations that I have. And my n plus 1th equation, which is here. Okay. So the solution to this n equations is represented by this curve. Anywhere on the curve, those n equations are satisfied. But I'm representing it in terms of some norm of x in a one-dimensional curve. Okay? But any point on this curve will satisfy f of xp equal to 0. And in addition, I want to satisfy this equation. As I said, that equation is the equation for a circle. Right? So here I draw a circle. That represents that equation. Right? So when I'm solving this n plus 1 equations, what am I solving? I'm solving the intersection of these two curves. That is either this point or that point. At those 2 points, the n plus 1th equation in green will be satisfied because it will be on this circle. And the n equations will be satisfied because it is on the curve. Right? Now, I can make this curve as big as I want. Okay? Suppose I am close to somewhere here. My current point is somewhere here. Okay, and I specify a circle that is something like this. Okay, so what this says is this point is at a distance s minus s naught measured along the curve. That is why it's called an arc length continuation. So this equation is a measure of the length measured along the curve. Okay, and so the problem will always be well posed because I will always have at least two solutions. Okay, of course, if the shape is complicated, you can cut it in more ways. You can have more solutions too, but you will never get into a situation where there is no solution past a parameter value of p. So if you give me s, I will solve for you what the p value is, because that is an unknown, right? And so that problem will always work like a charm, no matter how complicated the path is. Right? It's really a very, very powerful method for solving nonlinear algebraic equations when you have particularly multiplicities and stabilities. In your project, if you have that opportunity, I would say explore that. After Mrinal shows you how to implement this idea in COMSOL, you'll find that it will allow you to handle pretty complicated problems. Any questions? That's a basic conceptual idea, and we also have written the equations. What we need to do is now look at how we solve this n+1 equations using Newton method. Okay, how does the structure of the Jacobian look like? That's what we need to talk about. Any questions? Oh, Mrinal had some suggestion. Tom, question? I'm waiting for your question, Tom. It says Tom is typing. Oops. I need to increase this. So far, so good. Continuation part. Oh, no, are you a presenter? No, you can go ahead, Tom. If you have a question, just go ahead and shoot it now. Or anybody else? Anybody else? Anybody here has any question on this idea of what an arc length continuation is? Is it clear? Clear enough for you to implement it? Okay. Yeah, that's a good question. In fact, I was going to pose the same question. Like we talked about that there are two solutions. How do we know which one are we going to get? Okay, so that's a good question. Let's go back. So at any point, what you're going to do is there are two possible solutions. And you can use the Newton method to solve for the n+1 systems, but you can also apply the Euler-Newton continuation on that. What does that Euler-Newton continuation mean? It simply means take the tangent vector. Now the tangent vector is with respect to the parameter not p, but s. Okay, so you have a tangent vector at any point with respect to s. So dx, ds. Okay, that will give you the tangent vector. And you can take a plus delta s, which will take the measure of going in the forward direction, or you can take minus delta s, which will take you in the negative direction. So if I'm here and I draw the tangent vector with respect to s, if I take plus s, I'm going to give a guess which is closer to that solution. If I take a minus s, delta s, I'm going to get a solution that is closer to the left side. So you can control the direction with a plus minus switch. Okay. Does that answer your question, Tom? in a very superficial way, but we're going to develop these equations further.
Basically treat that as two cases. You try it for positive delta S, see if it converges, try for negative delta S and see if it converges.
It will converge both ways. So, and you'll put a
loop. If it converges to the same thing, then you only have one solution, right? Because you may not necessarily have two solutions, or three, or you may only have one.
You will, no, you will always have two solutions, because this is a quadratic equation, right?
Oh, that.
Yeah.
For that equation.
Yeah. So even if your solution that satisfies this equation is just a straight line, you draw a circle that intersects it, you will always have at least two. You could have more than that if the curve itself bends 2 or 3 times inside that. So you need to control the direction with your plus or minus sign. And if you use the plus sign continuously, you're always moving forward in the curve. So you trace the entire curve. And so you can, once you understand these tricks, you can then say, accidentally somehow you landed on a solution which is completely disconnected from everything else. Then you can say, okay, now I'm going to go backwards and trace the path backwards. Those kind of tricks you need to do if you have a solution structure like the one that I talked about, which is called an isola. Okay, suppose I have a solution like this, and then I have a solution that is isolated there. Okay, a branch that is isolated, it's called an isola. Okay, so you are marching along this, and somehow you made some mistake in your side. This is how you have to discover isolas, because they're disconnected, you won't know about their existence. So by some trick you get into that. Then you can say, okay, I'm going to go backwards, or I'm going to go forwards, and if you come back to it, you know that it is an isola. But if it just keeps on taking you to somewhere else, you know that the path never ends. So you need to terminate it at some point.
Sorry, what is dx, ds? What that?
Okay, the question is, what is dx, ds? So we are going to go back and formulate the problem properly and see how to solve this. Okay, so I need some space here. So I'm going to now talk about how to implement the Newton method on the extended system. Okay, so what is the extended system? The extended system is f as a function of x, which is treated as a function of the new parameter s, and p, which is treated as an implicit function of the new parameter s. Okay, there are n equations in there. Okay, and then I have an equation I call n, which is also function of x, which is treated as a function of s, p, which is treated as a function of s, but it is an explicit function of s too. This is the arc length equation that we talked about, that we just wrote down. There is a lot of degree of freedom in writing this. I just showed you a quadratic one. You can write other forms of this additional equations. It's an additional constraint that gets rid of the problem for us of a limit point. Okay, so we have these two equations. Do you understand what I mean by that? Okay, so I'm going to treat this as a new system f as a function of a new vector x and s. So this new function consists of this function f and this function n. Okay, and the new unknown consists of the vector x and the scalar p. So the length of this unknown vector is n plus 1. The length of this function is also n plus 1. There are n plus 1 equations in n plus 1 unknowns. What I'm trying to do is make it look like the original problem that we solved using Newton method. Okay, so all I have is a set of n plus 1 equation and n plus 1 unknowns. I'm introducing some new symbol. Instead of calling the original function as lowercase f, I'm calling a new function as script f, but it is nothing but the original function f and a scalar function n that I defined, a new function that I defined as a measure of the arc length. Okay, so that equation n is in one implementation the equation that you see here. Okay, this equation is what I call as capital N. It's a single equation, but it is an equation that depends on x, depends on p, and depends on s explicitly. Okay, and that's what I'm indicating symbolically as a function that depends on x depends on P and explicitly depends on S. But the original function, does it explicitly depend on S? It doesn't, because S is a parameter that we introduced, okay? So, but it does depend implicitly on S. Meaning, if I change S, I'm going to change P, I'm going to change X, and that means it will be affected. So these are coupled equations, okay? Coupled n+1 equations. So how would I apply the Newton method to this? Once you see this connection, the rest will fall into place, and that will answer your question of what is the meaning of dx ds, right? That's what we're trying to answer. So how would I apply the Newton method on this extended system? You can do that, but I'm just going to write it as, I have a new vector capital X, right? And that capital X consists of this X and P, okay? That at n+1 is equal to capital X at the nth iteration minus J inverse F. All I've done is expanded the meaning of everything. Okay, so this capital F is this n+1 functions. I know how to calculate them. Okay, and capital X consists of these vectors packed like this, X below that P as an unknown. Okay, and that is the Newton method, which is obtained by linearizing that set of n+1 equations. Right? Any questions on that? You should know at this stage how to write a program to calculate this capital J and the capital F. Anastasios must be laughing at my Greek symbols, which are all terrible, I think. I'm not writing it properly, but I hope you get the idea behind it. Okay, so this is your extended Jacobian, and this is your extended function. Okay. Please, if it doesn't make sense, if my symbol causes confusion, tell me. I'll try to go back and use something else. So I know how to calculate this capital F. All I need to do is calculate the original n functions and calculate the n+1 function that I have defined as an arc length. But what is the structure of this capital J, the script J or whatever you call it, the extended Jacobian? How will it look like? I'm going to do this in a block form. Okay, so this represents the first n equations, and this represents the n+1 equation as the last row. Okay, similarly, this represents the n variables, and this one represents the last variable. So, can you tell me what would go into this block? All the partial derivatives of all those functions, which would be the original Jacobian. That is the original n by n Jacobian. You have already calculated that. So by building on top of this, you will see that you can implement very powerful ideas with very little additional work, because I already have a function to calculate the Jacobian. What would go in the last row? The derivative of the last equation n with respect to every x, right? So here you will have dn dx1 all the way to dn dxn. That you can calculate because you know what the equation is. It's just a quadratic. You can take the derivative and construct that vector and pack it in the last row. What will go in this column? df1 with respect to p. That is the n+1 variable, right? So here you will have df1 dp all the way going down to dfn dp. Have we calculated that before? The answer is yes. When did we do that? For Euler-Newton continuation, right? If you go back, df dp here it is, df dp, that we calculated it already, that vector, right? So we can use that also. So what is the last element here? n dp. That also you can calculate because you know what n is. So this expanded Jacobian, which is n plus 1 by n plus 1, can be built using all the information that we have from the past, except the last row must be computed because that is a new equation we have added. So we need to calculate what those partial derivatives are and implement that. And I haven't still answered your question, Tom. We are getting there. Okay. So now we have built the Newton method for the extended system for the arc length scheme. So you specify S and you apply the Newton method, you will get a solution. Now the question is, if I have a solution for one value of S, how do I get the solution for the next value of S? Okay, and that's where you use the Euler-Newton continuation. Okay, now use Euler-Newton on the extended system. If you understand this idea, this is going to be used repeatedly in so many powerful ways for calculating singular points, etc. The notion of extending a system to implement an additional condition. Okay. In this case, the additional condition is I want to just turn around a limit point. Okay. So when you use the Euler-Newton continuation, it is going to be something like a capital X at S plus delta S is equal to capital X at S plus dx ds multiplied by delta S. Right? So now how do you get dx ds? Right? So this you know, your current converged result. This is the choice you're going to make for the next increment of the arc length distance, delta S. Okay? But how do you get dx ds? Apply the derivative to this function. Okay, f of x s is equal to 0. So it's exactly the same thing, we are repeating it in an extended system. So from this equation that you see here equal to 0, you can take the derivative of this with respect to s. Okay, let's see what that will look like. So use this function xs equal to 0 and take its derivative with respect to s. Okay, so it's going to be the f dx dx ds plus the f ds equal to 0. Now what is df dx? This is the extended Jacobian. We have already calculated it. What is df ds? That's a new thing that we need to calculate. Okay, what will that vector df ds look like? What will be the length of it? N plus 1, right? Because we have n plus 1 equations, and we are taking the derivative of every one of those equations with respect to s. But what is the derivative of the first equation with respect to s? 0, because first equation doesn't have s in it. None of the equations, original equations, have s in it, right? So these will all be zeros. Only the last element, dn ds, which is going to be minus 2s or something like that, because you have s minus s not square, right? So that is the only new element that you need to calculate. So calculate that, put it into this equation, solve for dx ds. Are you guys okay with me following? This is not a very simple task, but it's a very powerful task. But as long as you're comfortable with Taylor series, you should be able to follow, because really nothing more than that, except conceptually trying to understand what we are doing. Okay? So from this one, you can solve for dx ds. Because we have just calculated this we already know, the extended Jacobian. Okay? Tom, now is the answer for your question. What is who asked dx ds? You asked that question, right? What is dx ds? exist. So dx ds would simply be given as minus this Jacobian inverse of that multiplied by ds. What does it mean geometrically? What have we done to the problem? We had originally x and treated p as a parameter. Now we are treating s as a parameter. So we are plotting it against s. Okay. Originally, suppose we had the curve x versus p doing this. How would that graph look on this one? Think of that. The original problem had a graph that looked like this, x as a function of t, right? And I've reparameterized it and made p as an unknown and s as the new parameter. So I'm trying to plot the solution, same solution, with respect to s. How would that solution look like? What is s? The meaning of s is the distance measured from some reference point. So that distance is continuously going to increase along that, right? So that will basically unwind like this. It may be like this, but at every point there is only one solution in the forward direction. You need to fix the sign. Okay. So here I wrote it as plus, but you could have plus minus. If you put minus, you're going to go in the other direction. If you're going to plus, you're going to go in the forward direction. Okay. So I think hopefully that will answer Tom's question of the direction and your question of what dx ds is. Okay. Dx ds is the tangent vector on this curve. This is x, this is s. So dx ds is the tangent vector that is calculated from this equation. And that will have only one solution all the time. Okay, but the key is to recognize that s is a distance measured along this. So the distance is going to be a continuously increasing function. Okay. So if you plot, for example, p against s, what would happen for a curve like this? As you continuously increase s, what would happen to p? P would increase first, and then p will decrease, and then p will increase again. Right? So that gives you access to a very powerful set of methods, and these are not in packages like ANSYS, CFX, or Star CD or like that, but COMSOL allows you to implement this, and actually Mrinal figured this out, I guess very recently, how he can do it. So he will demonstrate that to you. The continuation method is simple Euler-Newton continuation is built into COMSOL. So you can just select that as an option and give the parameters, go for p from 0.1 to 10. And it will use a simple Euler-Newton. There is a tangent projection as an initial guess, and it will try to get you the solution. But if it is a turning point, COMSOL will fail. Okay? But what you can do is you can add this additional equation to COMSOL, and then it will follow the arc-length continuation. So you are implementing arc-length on top of COMSOL. That's why I like COMSOL as an educational tool. It really gives you the power to play with these things. And I will ask Mrinal to illustrate this on one particular problem. And I'm going to talk about the next assignment problem, and I want you to kind of implement all these things. And if you can understand this from this course, you have learned a lot already from this course, okay? Because this gives you a powerful tool for solving nonlinear algebraic equations. The next task would be to see how to convert differential equations into algebraic equations. Then all these tools will become available to solve ODEs and PDEs. So the problem I'm going to give you is the following. It's called the Bladder problem. Mrinal will illustrate it, all these ideas with two algebraic equations coming from a CSTR model. But the Bladder problem is coming from a combustion model. If you have coal particle and you're burning it, the model is governed by an equation like this: d square theta dx square plus epsilon e to the power theta divided by 1 plus mu theta equal to 0. Okay, and x goes from, let's say, -1 to +1. And the boundary conditions are theta at plus or minus 1 is equal to 0. That's called the Bladder problem. You go to internet and type Bladder problem, you'll find lots of information on that. It's a very classic model coming from combustion that applied mathematicians have played with it a lot. When mu, here epsilon and mu are the parameters. There are two parameters in the problem. Okay, x is the independent variable. X goes from -1 to +1, and theta is the unknown that we want to solve for. So we want to construct solutions of this type. This is x from -1 to +1. Okay, so let me ask you a simple question. Suppose epsilon is 0, what happens to the problem? It's a conduction problem, right? So the mechanism is, this is the conduction term. The first term is the conduction term. Okay, and this is the heat generation term. There is some combustion, some chemical reaction that is taking place, Arrhenius type of reaction. So theta is the temperature, and this is the heat of reaction term. Okay, and the heat that is generated is conducted away through the sides, and the ends are maintained at a temperature of 0. So if I turn epsilon off, that means there is no reaction. And the temperatures are 0 at the end, so the temperature is 0 everywhere because there is no uniform generation. So if you actually integrate it twice, you will get A theta plus B equal to 0. A and B are your integration constants. Subject to this boundary condition, you will find both A and B are 0. Okay? So the simple solution, this is what I said, for continuation method, put epsilon equal to 0, you'll get the first solution. Theta is 0 everywhere. Then increase epsilon. 0.05, 0.1, 0.2, etc. What you will find is the temperature profile looks like this. For each value of epsilon, epsilon 1, epsilon 2, epsilon 3, etc. That's a differential equation. So later on we will see how to convert that into an algebraic equation, but today I will tell you how it is done without really going back, going through the rationale for those arguments. Okay? Our goal is to solve this equation using something called finite difference method, and I will introduce the method hopefully today, we'll see. But when you construct the solution for this for different values of epsilon, suppose I said mu equal to 0, then it's simply e to the power theta. The nonlinearity is a little simpler. The solution for that problem looks like this. If I take the norm of theta, that is the average temperature for any value of epsilon, and I plot it against epsilon, what I will get is something like this. There are always two solutions. Okay? One low temperature value, one high temperature value. And up to a certain critical value, and this critical value is known. I think it is probably about 0.8 or 3.7, depending on whether your domain is defined as -1 to +1 or 0 to 1. There's a scaling factor of 2. Okay? So beyond that, there is no solution for this problem. People, in fact, have analytically solved that problem for mu equal to 0. That particular case, the solution looks like this. What happens if mu is not equal to 0? Then the solution can look like this. What happens if mu is very large? There is a critical value, I think probably around 4. The solution just looks like this. So the same problem can exhibit different type of parameters for each value of mu and each value of epsilon. So this is a two-parameter problem. Epsilon as a parameter, mu as the parameter. These are all the possible solutions. So it's a good test for us to see whether I can use the continuation method to turn around and explore the solution structure. So that's going to be your assignment, and this is what you should expect. Okay, there is a critical value of mu beyond which there is a unique solution for a whole range of epsilon. You need to find out what that critical value of mu is. And then when mu equal to 0, there is only one critical value of epsilon. For other values, there are two critical values of epsilon. Okay, so how does that critical value of epsilon change as mu changes? We will talk about that in the next class. Okay, so for now then, what you need to do is how to write that equation in finite difference method, and I will just sketch that. So the equation is d squared theta dx squared plus epsilon e to the power theta divided by 1 plus theta equal to 0. That's a differential equation. So we want to convert that into algebraic equations. The way we do that is replace this by something called a finite difference. So we're going to take our -1 to +1 domain, and this is what COMSOL does for you automatically, and divides that into several grid points, and each one is delta x apart, and I choose what delta x is. Okay. Then it turns out that the second derivative, d squared theta dx squared, can be replaced by something like theta I minus 1 minus 2 theta I plus theta I plus 1 divided by delta x squared. That is called the finite difference approximation for a second derivative, and it has a truncation error of order delta x squared. And we will see this later on. We will derive it if you have not seen it. If you have seen it, you are quite comfortable with that, right? So all you are going to do is, at some typical grid point I, you are saying that the derivative, second derivative, is related by the value at I minus 1, the value at I plus 1, according to that formula. So you replace that differential equation by the following algebraic equation: theta I minus 1 minus 2 theta I plus theta I plus 1 divided by delta x squared. And remember, delta x is something that you choose, okay? Plus epsilon e to the power theta I divided by 1 plus mu theta I equal to 0, for I going from 1 all the way to n. And you number your grid points such that this is I equal to 0, 1, 2, all the way to n, and then n plus 1. We number the end ones as 0 and n plus 1 because they are known. Okay? So all the interior points are unknown values. And you have n equations now. N equations in n unknowns. The n unknowns are the discrete values of the temperature at these points: theta 1, theta 2, theta n. So it is this algebraic equation that you need to solve in the parameter space of epsilon and mu, using Newton method, using Euler-Newton continuation, using Outland continuation, etc. That's going to be your next assignment, because I want to make sure that you understand how to grasp these ideas and implement them in MATLAB. With that, maybe we will wrap it up. In the next class, we will come back and see how to calculate the critical points where things turn around using the concept of extended systems again. And then with that, we will finish nonlinear algebraic equations. We move on to differential equations, dynamical systems, and then to PDEs and stuff like that, spatial discretization. Any questions? Minimize the chat window. Oh, I'm sorry. That's good. I'm sorry, I didn't pay attention to it at all. But Mrinal helped, okay? Any questions here? How do you find the pace? Am I going fast? Okay? You guys are okay? Overwhelmed after today?
Yeah, I'll definitely go back and watch this.
Yeah, there are a lot of interesting ideas there, I think.
That's a very clever technique.
It is, it is. It is a very clever technique. It's a very powerful technique. What reference material can I consult for nonlinear analysis? Ah, good question. There is a book. There are a couple of books. It is in the bibliography I have given. One is by Seidel. It's called Continuation Methods and Bifurcation Analysis or something like that. I will send the references again. Okay. And the other one is Nonlinear Analysis by Drayson. I've taken some of the material from there. So these two books should be fine. Mrinal will have, I think, also some papers maybe. Mrinal, do you have any suggestions for them? Yeah, there is a paper by Seidel, Role of Continuation in Engineering Analysis in Chemical Engineering Science. It's a review paper. We can probably download that and put it on Moodle for you guys. Okay, if there are no questions, expect an assignment sometime today or tomorrow and start working on it. I'll give you 2 weeks on this to work. Hopefully, incrementally, we will learn something, okay? And I think the numbers are dwindling, so maybe the class... Is the class getting difficult? Difficult? Somewhat. How about you? How do you find? Yes?
Today it was like
Quite difficult. Did I go through fast? Maybe do it again, and when you do the assignment, everything will sink in. It's very important to do an assignment on this concept. Okay? Are you okay? Was it tough today? All right. So, brief follow-up question from before. Could you add another equation to the circle equation to make it system n plus 2 instead of isolate only one solution along the arc length? I think the trend of the question is good. Instead of adding a circle or a quadratic equation, if you add a plane, okay, and there is another variation of this arc length equation that Keller proposed, then you get only one solution because you are finding the intersection of a plane with a curve. Okay, they all go by the name of arc length continuation, but the additional constraint, there is a lot of degree of freedom. But you won't want to increase it to n plus 2 to restrict to one of the solutions. I'm not sure how one would do that. I have to think about it more carefully. But the idea of making it only one solution is possible with a plane as a constraint. And if you want, I can show you how that equation looks like. I guess let me minimize this. If I can. And alternate arc length equation. I think it can digitize only at a certain pace. Write fast, it misses it. It would be something like this: W1 dxi ds multiplied by xi minus xi naught. This is an alternate version that Keller proposed, plus W2 times dp ds at the reference point s naught, multiplied by p minus p naught, equals s minus s naught. What is that? That is a linear equation. Okay, it's an additional constraint, but it's a linear equation. It still relies on the current reference point. Okay, and it relies on the derivative, the tangent. So you're taking, it's as if a tangent plane that you're taking in a hyperspace, hyperplane. And that also works very well. So you can use either of these two equations or any other equation. If you come up with your own equation, you can have Tom's equation for arc length continuation. All right, good questions. So don't give up. If it is getting difficult, let me know and I can go over it again. And by doing the assignment, I think you will learn quite a bit about this problem. Yes. Good luck. All right, guys. See you.
So for the assignment, you're going to just implement this on
I want you to implement the arc-length continuation on the Bladder problem. Okay, and I will ask Mrinal maybe next lecture to show you how to implement it on COMSOL. But I would like you to implement it on MATLAB because that's how you will learn most. You will have to figure out all the Jacobian for each case, and you'll see how the building process takes place from n dimension to n+1 dimension. And if you want, I will put you a sample code for another problem that we did in MATLAB.
Sorry, for the project, is the red one is something has already choose that, or is